My name is Phil Hands. I'm a Chancellor's Fellow and lecturer at the School of Engineering. I work in the Institute for Integrated Micro and Nanosystems, IMNS, up at the Scottish Microelectronics Centre, the SMC. Lots of acronyms. So I'm going to talk to you today about an area of my research called liquid crystal lasers. This big picture here is a liquid crystal laser, believe it or not. I'm going to try and hopefully challenge some of your perhaps preconceptions of what a laser looks like. Here's a laser in my hand here. It's bulky and plastic, and this is my liquid crystal laser made from liquids. And it has applications in a variety of areas which I'm trying to commercialise with various techniques, two of which I'll mention today briefly about anti-counterfeiting applications for security and also for next generation microscopy applications. So in order to understand what a liquid crystal laser is, I might have to explain to you first of all what a liquid crystal is. You may have heard of liquid crystals in terms of display technology. The laptop that's sitting in front of me here, and quite possibly the projector up there, will have a liquid crystal display. But what is it? The liquid crystal is actually just a phase of matter. So phases of matter that you'll be familiar with, solids, liquids and gases. There's a few others which are plasmas and Bose-Einstein condensates and things, but slightly more exotic. Solids, liquids and gases that we're all fairly familiar with. There's actually another state of matter, or a mesophase, called liquid crystal, which sits somewhere between liquid and crystal. But it only occurs in certain types of materials. These types of materials have what we call a shape anisotropy and an electrical anisotropy. What I mean by that is molecules that look a bit like sausages. It doesn't have to be a sausage. It could be other shapes, plates and bananas have been known to exist as well. But this molecule in particular here has a sort of sausage-like shape. It has a shape anisotropy, that's what we call it, so it looks different from one axis to another. It also has an electrical anisotropy, so it has a net dipole moment. It has a positive end and a negative end. That means when it comes close to its nearest neighbours, it likes to align and distribute itself such that it's either aligned or in some way self-assembles relative to its nearest neighbour. And we give this direction, so we call the director, so a vector which represents the orientation of the molecule. So rather than sausages, I now move my analogy to matchsticks. So a matchstick, that just represents our liquid crystal molecule. It has a plus end and minus end. Now if we heat up a liquid crystal, it goes into the liquid phase. And the liquid phase looks a little bit like this. My molecules are completely disorganised, jumbled around, they flow over each other, just like a liquid. And it doesn't matter which orientation I look at it, it still looks like a jumbled mess in every direction. So it is an isotropic and fluidic material. So if we cool that liquid down, all the way down to the solid phase, it might look a little bit like this. So now I've still got my anisotropic molecules, they're still long, thin molecules, but now they're rigidly attached to each other through strong covalent bonds or whatever it is in this crystal lattice structure. So now we have a solid material. It's anisotropic, it looks different in different directions, but it's rigid. So the liquid crystal sits somewhere in between, and extending my match analogy here, looks a little bit like this. So in the liquid crystal phase, the molecules still have alignment, they're all configured in the same orientation to each other, but yet there's a little bit of looseness there. The matches are still able to flow over each other, just like a liquid can. So we have a combination of crystalline structure, but yet a liquid fluidic nature. So that's what a liquid crystal is. Of course, those matches in the matchbox align in what we call a symmetric orientation. There's many different subtypes of liquid crystals, which I haven't got time to go through today. But this is a symmetric orientation where the matches, or in this case books, all align pointing the same way and occur in these little layered-like structures or shelves. I'm a bit more interested in the nematic phase, which is a slightly more disordered version of that. We still have an orientational direction, but we don't have the shelf-like layered structure. And this is the closest analogy I can think of here is a school of fish, all pointing in the same direction, swimming along, pointing the same way. The little extension of that is what we call the chiral nematic phase, or cholesteric phase. It occurs naturally in things like carrots. In fact, carrots were where it was first discovered. First ever liquid crystal was discovered in a carrot. And it also occurs in cholesterol derivatives that are in your blood and other various natural products. And what these chiral structures have, they're nematic phases, just like the fishes, but with each adjacent layer of nematic phase, the layer likes to sit at a slight angle to the previous one. So what happens is as you build up the layers, you start developing this helical twist in the director, this chiral nematic phase. And this is what's crucial to making a liquid crystal laser. If I take some chiral nematic material and I put it between two glass substrates to make a little liquid crystal cell, slide the liquid crystal inside, it looks a little bit like this. Except if you look at it in different angles of light, you start seeing these different colours, they're sort of pearlescent or iridescent type of optical effects. What's happening is that the sunlight, or whatever artificial light you've got, if it goes straight through the device, you see pretty much a colourless appearance, but at certain angles, if you catch the reflected light from the light source straight to your eye, you see colour, selective reflection of colour. We call this a photonic bandgap effect, and it's due to the fact that we've got this chirality at the nanoscale, which is giving us a colour reflection. It's colour through structure at the nanoscale. Now this occurs naturally in the natural world. These beetles, for example, and butterflies have this sort of iridescent, sort of metallic-looking luster to their wings or to their shells. And what it is, these beetles secrete a liquid crystal resin, which later hardens, but it self-assembles into this little nanoscale periodic repeating structure. And that, just like my chiral nematic liquid crystal, reflects certain colours and transmits other colours. So again, these colours come from this nanoscale chiral structure. So if we look at it in the lab, and we take one of these materials and we shine light through it, and we look at the different wavelengths, different colours of light that pass through these materials or reflect from these materials. So the transmitted light should be nice and flat if you've got a nice broadband white light source, but you see these gaps in the spectrum, these U-shapes. It's a photonic band gap. That accounts for the light that's been reflected from the substrate and is being shone and reflected into your eyes. So we can change the position of this band gap by changing the chirality of the structure. And when we tighten the twist up, we can add a chiral dopant to this, a chemical dopant which increases the twist, and we get a tighter pitch, and it blue shifts that photonic band gap, so we get a bluer reflection from our liquid crystal. If you want a red shift in the reflection, you add less chiral dopant, and you get a loosening of the helix, and it reflects red light. And you can tune that to any way you like in the visible spectrum, and indeed beyond the visible spectrum. Right, well, I've whittled on about liquid crystals and chiral nematics, but what's this got to do with a laser? How do I make a laser from these materials? Well, I have a quick checklist of what you might need to make a laser, first of all. There's a laser a bit like this, or here, this is a sort of a diagram of perhaps a helium neon laser, perhaps, or a ruby laser. You have three things in common. The first thing, well, the second thing, well, perhaps the first thing, most important thing, is the gain medium. You need something that will emit light. That's all that literally means. It's something that will absorb energy, emit light, which we can then use for lasing. And then we need to take that light and we need to resonate it backwards and forwards in some kind of cavity, a resonant cavity. And that's represented by the two mirrors either side of the gain medium. And they have to be positioned very accurately so that we resonate and amplify the exact transition that we need for our laser. And then finally we need some kind of excitation source, some energy going into the system. We can't get free laser light, unfortunately. So we need to excite it with some kind of pump source. It might be electrical energy, it could be optical energy. Quite often we shine flash lamps onto it or use other lasers even to generate the energy required to make this laser. So that's a kind of conventional laser. A liquid crystal laser has all of these properties as well, but in a slightly different form. So this is my liquid crystal laser. It's literally two pieces of glass, either side of a chiral nematic liquid crystal structure. So that twisted molecular structure that we described earlier, that gives us a selective reflection. We can tune that reflection to whatever wavelength we want by controlling the chirality. So what we do is we tune the reflection band to a wavelength that we want to emit laser light at. And then we add to it the gain medium. These have something that emits light. And that's the little red molecules here. We add to it fluorescent dye molecules, very common materials. And we choose our fluorescent dye molecule that emits light again at the laser wavelength we want, and then we resonate that fluorescence within the resonant cavity using our chiral structure. And that means all we've got left to do is to excite the system somehow. We do that, we shine a fixed wavelength laser onto it, something that is absorbed strongly by those fluorescent dye molecules. Those dye molecules then fluoresce, and that fluorescence is resonated in the cavity, which gives a stimulated emission. So very simple assembly for a liquid crystal laser. There's no external mirrors. There's no complicated alignment. It self-assembles into this structure. Very cheap, very simple system. There's a picture of one. You can see the two pieces of glass In between, 10 micron thick layer of liquid crystal. This is the pump light, the green light coming in, some green light going through, and the red light here, which comes out perpendicular to the substrate in both directions. If I want to, I can make it a single-sided emitter. I put a layer of aluminium on the back, make it reflective, and now we've got pump light coming in, some weighted pump light, and this red cone of light comes out, and this is a diffuse cone of light which we can collect and then use for something useful. And the picture doesn't do it much justice here, but one of the cool things about this is that if you look at the amount of energy going into this system compared to the amount of energy coming out through the laser-emitted light, it's about 60% slope efficient. So that's absolutely 1 or 2 orders of magnitude more efficient than any other laser system, which makes these pretty remarkable. So what if you want to tune the wavelength of your laser? Lasers come in all sorts of colours, but tunable lasers actually have all sorts of extra uses. Well, what I can do is make what we call a gradient pitch liquid crystal laser. So this has a red helical pitch at one side and a blue helical pitch on the other side, and this constant gradient in between, which is formed by diffusing these two mixtures together. So you end up with a reflection band that looks like this, which looks blue on one side, red on the other. And depending on where I fire my pump laser into the system, if I pump it down here, on the blue side, I'll get a blue laser. If I pump it up here, I'm going to get a red laser. If I pump it somewhere in between, I might get a green laser or a yellow laser. Any laser I want in that continuous band of tuning. So simply by translating this cell relative to my pump beam, mechanically moving it up and down, I can tune to any wavelength that I want in the visible spectrum. So here's a little video of a demonstrator system that we did just to prove I'm not just putting a leg here. This is a demonstrator system we built. It's got a gradient pitch laser in there. We put a little hologram on the end, so it's projecting a little radiation symbol. It's not significant. There's nothing radioactive here. It's projecting a red laser light, and then we translate that gradient pitch across the pump beam. We tune, in this case, from red through to green. And it passes through all the intermediate colours, all the oranges and yellows in between as well. So not only can you, so that looks a little bit like a normal laser, apart from the fact it changes colour. That's pretty useful. But one of the other cool things about liquid crystal lasers is that we can very easily manipulate the way in which the light emits from the system. If we want, we can have arrays of lasers coming out very simply. Instead of focusing a single spot onto this cell, focus 100 spots on. And where every spot happens to be, we'll have a new laser source from that point. So it's very easy to make large area emitters, or even then combine these up for higher power lasers as well. We can also do what we call polychromatic arrays, multiple colours simultaneously being emitted from a single source. That's now very interesting. Lasers conventionally, like this one, press the button, a single colour comes out. Tunable lasers, conventionally, press a button, one colour comes out, maybe you can change the colour. But there's no systems really out there that can do many colours simultaneously with the same system. And of course we can use laser light to do all sorts of really cool stuff. These are holographic projection images, 2D holograms, projecting little pictures of an eye. Obviously change the colour. So there may be some applications, future applications in holographic TV display systems. 2D and 3D. When we say holograms, we don't just mean cool 3D stuff, 2D also as well. Now, one of the problems with in order to do holography, you need to use usually a monochromatic laser-type light source. But most lasers, when you shine them through a hologram, this is our trusty radiation symbol hologram again, you get this speckle effect here, and that's due to the very narrow line width of the laser that you're using. The narrow line width gives you a nice, clear image, but it also gives you this speckle. We could use an LED instead, which has got a broader line width, but that gives you a nice, gets rid of the speckle beautifully, but of course it fuzzes out the hologram completely so you can't really see it anymore. The liquid crystal laser, on the other hand, has a nice compromise between the two. It has enough coherence to give you the holography to make a nice high-resolution image, but not so much coherence that you generate the speckles. So you get very high-quality images in your holographic displays. Sadly, at the moment, the laser is not powerful enough to be able to be projecting large areas holographic displays, but we can certainly do this on a small scale, and so maybe this is direction for the future. So here's my demo laser again. I can colour tune anywhere from 450 to 850 nanometers. That's pretty much the whole visible spectrum. These are my cartridges that I can insert in. I can put in whatever laser wavelength that I want to, throw it away like an ink printer cartridge might do. Just select whichever wavelength you want. Alternatively, I can put in one of these colour tunable gradient pitch cells and continuously tune over a certain wavelength range. Plus, I can also put in arrays and things so I can get multiple colours simultaneously. I'm trying to now use these lasers into something that's perhaps, as an engineer, I want to make these things useful, actually produce something that utilises these unique properties of liquid crystal lasers. This is an image from a fluorescence microscope. I'm not a microscopist, so apologies if I get some of the details wrong here, but confocal microscopy, fluorescence microscopy, these techniques are used often in biology, biomedical research especially. This is an image through a microscope of a biological, I think it's some nerve cells, I think, in the brain. And what we do is we stain this sample with a bunch of chemical fluorophores, these dyes, which are each attracted to certain biological elements in the image. And then these fluorescent dyes, when I excite them with a laser, will emit fluorescent light and light up the appropriate parts of the image. So we can use this to identify tumours, for example, in biopsy samples. So this image has actually had to be a composite image. We've had to image it first of all with one laser, where we raster scan it across, make all the blue bits light up, and then we do it again with another laser, raster scan, make all the green bits light up, and so on, until we build up this composite image. Now the idea is that we could perhaps use a tunable liquid crystal laser to create all of that image in a single shot. We could direct light wherever we want to, and whenever we want to. These are the type of systems that we have. This is a fluorescence microscope from Leica, and here's a confocal system. They're big, bulky systems, and in fact they're even bigger than you can see, because underneath the table or in the room next door is a bank of 10 or 20 lasers sitting there in a box, each of which in turn is illuminating our fluorophores. So I would say throw away that box of lasers, replace it with one of my lasers, and you can get the whole system much more compact, perhaps even portable systems as well. Much cheaper as well. The other big advantage of using a tunable laser system is here are all the fluorophores that you might be staining your samples with. If you look at the excitation spectra of these fluorophores, they often have a significant overlap. So there's a crosstalk. When we excite one fluorophore with a laser, we often excite a neighbouring fluorophore at the same time. That's not very good, because then you're not sure what you're really looking at. It's because most lasers, like the one in my hand here, are only available at very fixed, very specific wavelengths. You can only buy a Heaney laser that emits at 600 or something nanometers. It's very difficult to find other wavelengths. With this tunable laser technology, you could dial up any wavelength that you want. So if you want to excite, say for example, this yellow spectra here only, and not the neighbouring green one, then you need to tune your laser to right to that fluorescent spectra, emission spectra there, excitation spectra there, and it will only excite that one fluorophore. So you can be much more specific in your images and use more fluorophores simultaneously in your image. So hopefully push forward the boundaries of microscopy. And finally, I'd just like to mention also, one of the new developments of the liquid crystal lasers technology was that we could actually now inkjet print these lasers down. So formerly I showed you two pieces of glass substrates with liquid crystal held between them. That's a pretty simple system, but we weren't happy with that. We thought, well, let's see if we can make it even simpler to make. First of all, we made a paintable laser where we mix all the ingredients together in a bucket with some polymer, and we paint it down onto the substrates, and it dries, and it lasers. That worked. But I thought, well, let's take it a step further. Can we print and pattern these lasers arbitrarily? And we can. It takes a little bit of preparation. We need to prepare the surface with a wet polymer layer, and then we inkjet print our dye-doped liquid crystal into the wet polymer layer, so that we have a kind of a semi-embedded crater, a little droplet of liquid crystal that forms in the system. And if you look at this, it means that when you shine light on this droplet, it will emit laser light at whatever wavelength you programmed it to do so through the mixture of the relevant ingredients inside this inkjet printed drop. So what we can do now is start printing patterns like this. This is a work I was doing in Cambridge before. That's the request of the university. You inkjet print our liquid crystal lasers down onto an arbitrary substrate. In this case, it's a piece of plastic. And because it's the chiral nematic liquid crystal, it has that selective reflection, that reflection band. We can see this kind of metallic-looking iridescent image. So we can use it as a security coating, because the exact colour of reflection is going to be determined on the exact helical pitch of that chiral liquid crystal. And that's very difficult to replicate, because it's so intrinsically dependent on the small concentration changes. And also, it's circularly polarised because of the chiral nature of that reflection property. It means that if we put a circular polarizer over the front of it, we can either remove or make visible that security feature. So that's a kind of a covert or overt, should I say, security feature. You might put it on a high-value goods like a bottle of whiskey or a tax certificate or a cheque or something like that. We also paint them onto other materials like this, metal, glass, paper. And this thing here, what we've done is simulated, it's actually a little QR code, I think, but it's a bit like, the idea is we might print banknotes with it. I don't know if you've ever been to a shop and paid for something with a banknote, and sometimes if they think you look a bit dodgy, they might stick the banknote under the UV light and you see these inks fluorescing. So what they're looking at there is inks with fluorescent signatures in them, and they're just checking the ink's genuine by seeing if it fluoresces. So you can do the same with this. The ink within the liquid crystal laser, the dyes will fluoresce again, but crucially, these ones will actually laze. So if we can get a laser to come out of your banknote when you stick it in, it's not a powerful laser, it's not a health risk or anything. Put a laser in there, it means that we have a very narrow single line width, single wavelength laser emitted from your banknote. In fact, why not have 10 lasers coming out of your banknote from different inkjet printed drops all over the banknote? So the spatial location of these lasers and the very fine tuning control of the wavelength of those lasers gives you a very unique optical signature for that particular note, which is incredibly difficult to copy. So we spun out a little company to do this and to market this and to sell it, which has since been sold on. So hopefully soon we'll see some of these products on the market. So that's the end of my talk. Hopefully I wanted to tell you a little bit about liquid crystal lasers. The science has been developed for a number of years. Now we're working on the engineering. Hopefully we'll have some product. We've already got some products hopefully coming onto the market relating to anti-counterfeiting applications. I'm now working on the microscopy applications, and perhaps in the future we'll also have some holographic TV applications as well. So thank you very much for your attention.
This production is brought to you by the University of Edinburgh.